Swayam Prabha. Digital India. Educated India.
All right, good morning, everyone. I'm going to talk about things, and I wasn't sure what the audience would be. So I know we have a broad mix. We have all the way from assistant professors to second year mechanical engineering undergraduate students to, so it's a wide cross section. And I'm not sure if, and my talk, and I wasn't sure what the makeup of the audience would be. So my talk is very much research focused. It's focused on stuff that we've been doing. But I'm going to try and make it simple enough at the risk of maybe boring some of you who think it's too elementary. And sometimes it may, for the undergraduates, it may seem it's over the top. So I'm going to try to stay somewhere in between so that at least if you're an undergraduate student, a second year undergraduate student, you walk away with a basic understanding of what this process is or what the underlying science is at a high level understanding. And if you're somebody who's a bit more deeper into research, then of course you can appreciate some of the things I'll talk about. But I want this to be interactive. I don't want this to be me just lecturing and you asking questions at the end or not asking questions at all. It's very boring for me to stand here and have nobody ask me any questions. If there's no interaction, it's not clear to me you're understanding anything I'm saying. So please raise your hand, stop me. In my opinion, it's not critical that I go through every slide. If you don't understand 90% of what I say, it's pointless, right? You would have wasted your time and I would have wasted my time. So I think it's important that you stop, ask me questions, and I'll try to explain to the level that makes sense for you. Okay, I'm going to try to do my best. Professor Samuel actually gave you an overview of broad range of manufacturing technologies all the way to including measurement technologies and more recent developments in AI, machine learning, and digital twins, and so on and so forth. So, hopefully all of you here, all the way from the undergraduate student to the young faculty member, have a basic understanding of manufacturing, right, of basic processes. And if that is not the case, let me know. So hopefully all of you have some basic level of understanding, and maybe you have had workshop practice. At least the second year undergraduate students would at least have seen the machines, have some understanding of what these processes are. And so with that in mind, I'm going to start. And this topic is going to be, it says surface modification. This is an area that we worked on for the last maybe a little more than a decade or more, actually. And much of it was driven by interest expressed by manufacturers and of safety critical components. Okay, and Professor Samuel showed you pictures of a jet engine, for example. Very complex system. Obviously, it's a safety critical. It has safety critical components, all the way from the turbine blades in the hot section or the cold section. Those are all critical components. They're subjected to very high temperatures, extreme stresses over a wide range of temperatures, and so forth. And these types of components have to have certain properties, right? As mechanical engineers, we focus on designing something that meets a certain function. So in this case, the function is, let's say, a compressor blade or a turbine blade for one of the engines. And it has to meet certain requirements, right, in terms of the loads it will withstand under certain environmental conditions, etc. And so for those types of components, those requirements are pretty extreme. As Professor Samuel mentioned, aircraft accidents are very few and far in between. You don't see them. Hopefully we never see them, but unfortunately we do occasionally see them. And consequently, but fortunately they're very minimal. That's because these are highly engineered systems, right? So one of the technologies that actually is utilized for such safety critical components is a class of technologies that are called surface modification technologies. It's a class. There are many types of surface modification technologies where you modify the surface that you might have produced using one or more of the basic manufacturing or even modern manufacturing techniques that you heard from Professor Samuel, right? Whether it's machining, subtractive manufacturing, or if it's additive manufacturing, whether it's a metal, in this case, primarily metals. These types of safety critical components are metallic, typically, the jet engine components. And so once you have produced them, you need to do some post-processing on them in order to achieve the properties that you need, such as, let's say, turbine blades for a jet engine, okay? And so surface modification is used there. Of course, surface modification is used for many other things. So let's get into it. Let's talk about, and I'll talk specifically about surface modification using one method that we've focused on, but I'll give you a quick overview of some of the other methods as well, right? So need for surface modification. I've already talked briefly about the need. I'll give you some examples. So this is kind of the outline of what I'm going to do, cover. So as I was saying, some of these components, aircraft components, for example, and you see the jet engine component shown there. You see the blades on the right in that slide. It says fretting, fatigue, failure. Fretting is a kind of a tribological process where you have two surfaces normally loaded in contact and subject to relative motion, typically cyclic motion, right? Such as a ball bearing against a raceway or a turbine blade. These blades are actually mounted in slots. Okay, they're called fir tree type of slots. They're actually inserted in there. So it could be that you might encounter fretting fatigue because of that. You don't want any relative motion, but it can happen. So there's a failure. These blades can fail. That's a catastrophic failure, by the way. If you're flying a plane and if that happens, that's a bad thing. It should never happen. Rarely it happens, but it does happen occasionally. So that's a turbine blade example where it failed because the properties that it was designed for and manufactured for were either inadequate or the environment or the operating conditions exceeded what you designed it for and produced it for. Fatigue failure is common. Any kind of surface that's subjected to cyclic loading, right? Whether it's mechanical cyclic loading or thermal cyclic loading or some other type of cyclic loading. Eventually, there are so many, it's designed to withstand certain number of cycles before it fails. Hopefully, those number of cycles is well beyond, the life of that component, right? That's how you want to design them. And finally, it shows you some pictures of what is called stress corrosion cracking failure. You can have marine components, let's say propellers of a turbine that is used for a ship, for example, right? It's in a saltwater environment, right? It's also being loaded, but it's an environmental condition which is very different than up in the air, like 30,000 feet. So you can actually accelerate failure of such components under stress, but in a corrosive environment. Salt water in a sea environment is corrosive, right? And depending on the materials that have been used, it can fail. So these are the reasons why we need to somehow modify the surface to avoid these types of failures, right? That's the motivation for surface modification. Now, there are many ways to modify surfaces, right? So obviously, Professor Samuel did a great job of telling you about many different manufacturing processes. You produce the component. Usually, these types of products that are components that require surface engineering, you require more than just the manufacturing process. You produce it, and then you may have to subject it to some other steps, right? Such as the surface modification process I'm going to talk about. So there are many types of surface engineering processes. Typically, the goal here is to achieve a certain type of surface quality, both in terms of topography, geometry, microgeometry, typically, as well as near surface properties, mechanical properties, whether they're tribological properties such as friction, wear, lubrication, whatever the tribological phenomenon is that's actually relevant to that application. To mechanical, subsurface mechanical properties. Some of these fatigue failure failures happen because a crack initiates just below the surface and propagates, right? Or a ball bearing fails, spallation occurs, things of that nature. So there are many ways to actually modify the surfaces. You can see here, there's ways to do surface engineering where you don't alter the chemistry, right? Where you don't alter the chemistry. And this is what we will focus on, where we are trying not to alter the chemistry. But there are also processes where you will alter the chemistry. And sometimes that's desirable, okay? Where you might alter the chemical composition of the near surface layer. You might do that by producing some sort of reaction with some environment which produces a certain chemistry in the top surface which gives you the properties of interest, right? Or you can coat. Coating is a common thing, right? Many things we use coatings to either to enhance wear resistance of the component or whether they're cutting tools, where there are many, many different applications, or whether you're coating it to protect it from some environment, etc. Okay? But there are processes, surface engineering processes or surface modification processes where you don't alter the chemistry. And there, again, you have either thermal processes where you actually bring about microstructural changes. Keep in mind that most of these mechanical components, you as even second year engineering students, you learn about mechanical design, right? Mechanical design is all about designing a component, geometry, properties. What allows you to achieve those properties? Properties are achieved by the structure, by the microstructure. So that's why people talk about process that is used to produce the shape, but the process also produces certain microstructure in the material, okay? And that microstructure is what gives you the properties. So process, structure, property, relationship. It's not just process and property, okay? There is a connection through what happens inside the material. And so that microstructure is very important. So you can actually change the microstructure thermally. Professor Samuel talked about laser processing, where lasers, basically photons emitted by a laser interact with the matter, solid, right? You either can ablate it, vaporize it, or you might alter the microstructure as well without producing any ablation, okay? That's also possible. So that's a thermal process, for example. Mechanical processes are what we're going to talk about. So a class of processes that are used to bring about such surface modification and alter the local microstructure. Again, we are talking about making changes to typically the near surface region. You've already produced the component using one either additive process or a machining process or a forming process, whatever the case may be. You produce the bulk material, bulk shape, the actual shape, all of that's produced, but you want to impart certain properties in regions that are going to be subjected to very high cyclic load, for example, such as a turbine blade. You don't want it to fail, and failure typically occurs in the highly stressed region. Only in that region I want to modify the properties, right? And so typically it's the near surface that needs to be modified. So that class of processes is called peening. Peening is the name, okay? P-E-E-N-I-N-G. And it has been around for a long time, okay? The simplest way to think of peening, there are many types of peening technologies, but the simplest thing I can give you example of is where you basically, if you think of shot blasting, how many of you have some understanding or understand what I mean by shot blasting? Okay, so where you basically subject a surface to mechanical shots, okay, which could be pellets, right? Steel pellets, ceramic pellets, whatever the case may be, hard material that is impacting the surface and produce localized deformation, okay? Permanent deformation. Yes?
How do you basically identify whether the process will be thermal or mechanical?
How do you identify?
Whether the process to be carried out will be thermal effects or
No. So that depends. That depends on many factors, okay? For example, sometimes you can do both. And there may be non-technical reasons for you to pick one or the other. So for example, laser shock peening. Professor Samuel mentioned laser shock peening. You can use lasers, and this is one of the processes that you see on this slide, laser shock peening, to achieve the same end effect, right? To modify the surface. But it has its advantages and it has its limitations. And sometimes the limitations for your particular application may be such that you can't use it. Okay? So if you can use it, that's a thermal process for you to modify the, okay? Whereas in your case, you may either not have a laser system that can do it, or you might say that it's too expensive. Whatever the case, there are non-technical reasons that can drive it. Sometimes there are technical reasons, okay? Because that material cannot be subjected to the kind of thermal temperatures that might be generated, because it will damage the material below the surface, okay? So it's a good question. There is not one simple answer to it, okay? All right, yes?
So chemical vapor deposition comes under which category of these?
So chemical vapor deposition would be a surface modification technique, okay, depending on whether you're trying to use it for coating. So typically CVD is used for coatings, right? Very thin, nanometric, a few tens of microns thick coatings on cutting tools, on other types of products that CVD would be used. CVD can also be used for producing diamond, for example, right? You can do many things with it. So yeah, CVD would be a coating type of technology, okay? But anyway, yes?
Sir, what process you undergo to estimate that there should be a surface engineering to be done here?
That's what I said. I think it depends on the application, right? If in most of these processes, I'm talking about peening processes, the objective is to enhance the fatigue life, okay? So if this component is going to be subjected to fatigue loading, whether it's thermal fatigue loading or mechanical fatigue loading or some combination thereof, then you need to engineer it such that it can withstand those conditions. Then you know that you need to do it. Now, whether or not you need to do it depends on the application, depends on the component. If it's a turbine blade, yes, you probably need to do it. Or not probably, you need to do it, because you want to enhance the fatigue life, right? Not wear, it's typically fatigue life. You don't want it to fail. You don't want a fatigue crack to initiate and propagate and cause catastrophic failure of your blade. Then the whole engine fails. I mean, any kind of a blade failure in a jet engine is catastrophic, because these things, if you're flying and a blade disintegrates because of fatigue failure, these blades will go flying, they'll tear through the engine completely, through the encasing, and can even actually damage the plane and bring the plane down. That's catastrophic. You can't afford it, right? Nobody wants to fly in a plane like that. I certainly don't. So you have to engineer it such that it won't happen, okay? That's when you use surface engineering. Now, peening technologies in particular, but there are other types of surface engineering methods like CVD, right? There, it's not fatigue failure that is driving it. Okay, it could be coating, wear resistance, friction reduction, etc. Okay, typically tribological and fatigue are kind of the drivers, if you will, for most of these surface engineering techniques, right? And at different length scales. Okay, so just to make sure that I don't get hung up and I cover only 5 slides, because when I lecture, I might only cover 5 or 6 slides and spend the entire hour and 20 minutes lecturing, so we want to be careful. So there are many different techniques. One of the oldest methods is shot peening. Shot blasting, same idea, okay? Where you take, and this is still used in industry, aerospace uses it extensively, which is essentially taking a peening media, in this case mechanical shots, either mechanical steel balls or something like that, or ceramic could be, and different shapes, that basically you bombard the surface in the region of interest where you want to impart compressive residual stresses. Professor Samuel mentioned briefly residual stresses. I want to make sure everybody understands, certainly the second year undergraduates need to understand it. I know that some of the graduate students understand it. What is your understanding of residual stress? Obviously, you understand stresses, right? When you design something, you apply a load, you're stressing the material, some stresses are generated, right, inside the material. It could be normal, stresses, shear stresses, etc. that are generated. Both are generated typically when for any kind of load application. What about residual stresses? What is your understanding of residual stress? What do we mean by residual stress? How about our undergraduate students? You want to take a guess? What do you think? Think about what the word means, residual stresses. Yes?
When a metal is formed in a desired shape,
Mhm.
there exists some metallurgical changes in its geometry
Mhm.
and it imparts residual stress in the surface.
Okay, fair enough. That can happen. You can have stresses when you modify the surface or you produce a surface using some process, right? But why is it called residual stresses? That is correct. Okay, so what it means, residual stresses means when you apply a load, obviously it's stressed. When you remove it, remove all loads that were applied to it, mechanical, thermal, whatever the case may be, it still has some stresses. So these are elastic stresses in the body, right? And typically you have to deform the material inhomogeneously. That is, you have to produce plastic deformation, okay, go past the yield point, deform it, then release the load. Then obviously the elastic stress will recover the elastic deformation, but if you're doing plastic deformation, you will still have permanent deformation, right? Now that permanent deformation is essentially represented in the form of change in shape that the object went through. But there will be residual stresses in the material that are because of different amounts of strain that different parts of the material went through, plastic strain, and so eventually there'll be elastic stresses. Okay, why did I ask you that question? Because the goal of these peening processes, particularly for these types of applications, is to induce compressive residual stresses. Professor Samuel talked about residual stresses being bad. Tensile residual stresses are bad, okay, for these applications. Because if you have tensile stresses already in the body and I apply additional tension, right, it'll fail much quicker, right? Whereas if I impart compressive stresses in the body and I apply tensile stresses, first I have to overcome that compressive stress that's already in there and then exceed the yield point, right, or strain the material past its yield point, only then it'll fail. So that's the idea. So I want to modify the surface, induce compressive residual stresses such that when it's subjected to such tensile loads, and think about a blade, it's rotating at high speeds at elevated temperatures and sometimes in corrosive environments too, right? And what happens when you rotate? There's centrifugal forces acting, right? High loads are acting at elevated temperatures. So therefore, tension is there. So obviously you want to put compressive stresses such that, it will take a lot more tensile stresses for it to fail eventually. That's the idea, okay? That's why you use these processes. So shot peening is the oldest process that's out there. Probably back in, it dates ever since people understood that when you strike something with a hard object, especially a metal surface, you're going to deform it plastically in a localized manner. That's the idea. That's what you're trying to do, and by doing so, you impart compressive stresses. The challenge with this is it's a very flexible process. It's used extensively, but you're streaming a bunch of shots at the surface. Hard to control that process, okay? Also, it's a high-cost process, and more recently, it's not a very sustainable process. These shots, when they get worn out, they're thrown in the landfill. You cannot recycle them and reuse, okay? Obviously, from an environmental standpoint, it's not a very good thing for us to do that, is to keep throwing away things. So this is part of the motivation for why we looked at the process I'm going to talk about. I want to make sure that I'm not going too slow. Laser shock peening is the same idea. All of these processes, with the exception of deep rolling, are the same idea, where instead of using mechanical shock, as Professor Samuel mentioned, you use a laser. Laser is what? Everybody here knows what laser is an acronym. What does laser stand for?
Light amplification by stimulated emission of
Radiation. So you're generating radiation, right, of some wavelength that interacts with the medium. So in laser shock peening, either you can subject the surface of interest to these coherent stream of photons emitted by a lasing medium, and the interaction between these photons and the electrons in the material will actually generate heat, right? And that's what happens. That's one way. But the way that Professor Samuel talked about, he showed you a video where there was liquid, right? So the workpiece is put inside the liquid. You have this laser interacting with the liquid medium, generating a shock wave. That shock wave is what acts like a mechanical shot. So instead of using a mechanical shot, you have a shock wave that actually interacts with the surface, and it's strong enough to actually plastically deform the near surface region of the metal. So it produces the same end effect. It's just a different way of generating that effect. Okay. Obviously, it has its advantages too. Some people use it in the aerospace industry. The one advantage is it can produce residual stresses that are deeper. When I say deeper, how deep is deep, right? Typically, these types of stresses, generally, depending on the material, depending on the application, you're talking of on the order of few hundred microns, right? So let's say half a millimeter, maybe. If you're good, that's good. Half a millimeter is probably adequate. Certainly less than a millimeter, typically. That's the thickness of layer of material that you're actually modifying the properties and imparting compressive stresses, okay? That's the objective, residual stresses. So, laser shock peening, depending on the strength of the shock wave that can be generated, can produce deeper stresses, that are the deeper level, which can be a good thing depending on the application, where that material is being subjected to loads that produce stresses much deeper into the material than you want, much compressive residual stresses deeper into the material to kind of extend the life of that component and prevent failure from occurring due to tensile loads, right? So, but it's higher cost process. You need a laser system. You need to prepare the surface. In the example that Professor Samuel showed, you need to submerge this in a medium. So think about a large jet engine component. You have to submerge it in a tank of water or something like that. It may be sometimes impractical, right, or difficult to do. Longer processing times also, okay, compared to having a stream of shot just being bombarding the surface. There are other processes like deep rolling. Okay, deep rolling is rolling. Most of you understand rolling process, right? Where you take a roll, typically a hardened steel roll, and you apply, you roll the surface, right? Just like you might make chapati at home or something, right? Same idea, but of course it's not soft material that you're rolling some metallic material. So you apply loads, you can apply very high loads depending on how you design the roller geometry, etc. And you can produce very high, deep compressive residual stresses. Okay, and this is deep rolling type of processes are used, but generally for smaller components, not for very large components. Okay, it's harder to do. You also need high loads, specialized equipment, and so forth. You can generate very high compressive residual stresses, very deep compressive residual stresses, and very good finish because it's like a burnishing operation. It's almost like a polishing operation in a sense. You're not removing material, you're simply flattening any surface asperities that might be there and produce a very shiny surface you will produce in rolling. Okay, I said part geometry limitations, small parts generally is okay, works well. Water jet peening is another technology people have experimented with. To the best of my knowledge, not too many people use this in practice, okay? I will talk about, I know the title in your schedule says water jet peening. I'm not going to talk about water jet peening. I'll talk about a variation, a different process, but still using water to peen, okay? So water jet peening is where you essentially make use of the hammering impact of water droplets. You generate high pressure water, right? Very high pressure. You require very high pressure. And the water droplets impact the surface. Instead of mechanical shots, you have drops of liquid that are impacting and essentially deforming the surface and generating compressive residual stresses. Nice thing about it is no surface contamination. Water, right? It's water. It does not use a mechanical shot or something else. Also relatively inexpensive. Water is available. Yes, water is an important resource, but I can recycle water, right? I can recycle, I can filter it and recycle water. So it's more sustainable medium. The challenge is it requires very high stress pressures to generate sufficient hammering impact loads or hammering type of effect. And it doesn't, to the best of my knowledge, it doesn't do a very good job actually in terms of generating compressive residual stress. People have tried it, okay? To the best of my knowledge, nobody uses it. All right. So that the motivation for us to look at an alternate technique, okay, which is called water cavitation peening. So what is water cavitation peening? I won't go through everything on this slide. The point I'm going to make here is that I'll just justify why should we even look at this process, right? Why do we need a new process? There's at least 4 that I talked about. They exist, right? Because in general, it's not just a matter of residual stresses. Residual stresses are, of course, key to extend fatigue life. But other factors are there. Surface finish. Fatigue life is determined not just by compressive stresses. It is also affected by surface finish. If you have a rough surface, then those roughness peaks on the surface can act as stress concentration points and lead to failure. So you need to balance all of these things. Also, if the surface has been cold worked, how many folks understand cold working? Undergraduates, I want to make sure. I know that the graduate students understand it, but what about undergraduates? Understand what cold working, hot working, warm working. You're working the metal, you're deforming the metal at different temperatures. Cold working would be under room temperatures, right? Plastically working the metal is what we are talking about. So if the metal's already been cold worked, what have you done to the metal? What does it mean to say that I have cold worked the metal? Deformed it. But what does deformation do to the material? I'm sorry? Say that again? No thermal stress is acting. No, what I'm trying to ask you is, okay, why did they change? What did you do? By deformation, what do you mean? Dimensions change. Okay, so fundamentally when you deform, you're straining the material, right? And the constitutive properties, stress-strain relationship determines how you stress the material, right? So you're straining the material, right? That's what you're doing. Cold working it, you've already imparted some strains into the material, right? So if it's already strained, and if I apply additional strain on it, additional deformation, there is a limit to how much you can strain the material, right? Every metal has some finite limit. Beyond its fracture strain, it cannot withstand any additional strain. So if that's another factor that matters. You can't strain it anymore if you've already pre-strained it. That's the point I'm making with cold working here. Or any kind of work hardening that you might have done to it. Material response to surface treatment. Not all materials will respond the same way. Okay, so that matters. What is it that you're actually peening? And the stability. So residual stresses can actually relax over a period of time. So there's relaxation effects that one has to be concerned about. You might impart certain compressive residual stresses. Over a period of time, those stresses may decay a bit. They'll equilibrate and adjust, and that is another thing you have to be concerned about, okay? So there are reasons to look at alternate methods. But practically speaking, cost, flexibility, processing time, safety, these are all other factors that in practice people want, okay? I mentioned shot peening is used in aerospace industry. People throw the shot away to a landfill. That's not a good thing, right? That could be a reason why I focus on some other process. Okay, so we need an effective, flexible, inexpensive alternate process to shot peening. That is what motivated us to look at it, okay? And we looked at it because we had a sponsor who actually came to us, okay? An aerospace company that actually we worked with. Now, I'll explain the very high level understanding again, and for those who actually have a deeper level of understanding can ask me questions and I'll try to answer. But I'll try to keep it at a level where I don't lose interest of a lot of the undergraduate students as well that are here. So what is the principle of cavitation? How many people here understand what cavitation is? Or at least know what cavitation is? Yes. What is your understanding of cavitation?
So basically cavitation is due to some stresses making a cavity in the surfaces.
No, so that's not the cavitation I'm talking about, okay? cavitation phenomenon is basically a phenomenon that occurs in fluids. Okay? Fluids will cavitate typically, although gases can cavitate too. Okay? So what does cavitation mean? There's a definition up there on the slide. It says the appearance of vapor cavities. So think of bubbles, air bubbles forming in a column of water. Okay? So let's say I have water with no air bubbles in it to begin with. But depending on how I actually deliver the water, I might generate vapor bubbles. Okay? If you generate vapor bubbles, and the vapor bubbles in cavitation form inside initially a homogeneous liquid medium, such as water, it could be any other medium as well, due to local reduction of pressure. Okay? So the pressure in the flow drops, okay, and there is basically a vapor bubble that forms. Okay? And think of not just one bubble, hundreds and thousands of bubbles forming. So that's the phenomenon of cavitation. It occurs, people realized that it occurs because they found that ships, the propellers of ships, etc., were wearing out very quickly, they were wearing out. And ships are obviously, these things are rotating in water or in saline water, obviously. And the wear process was due to cavitation, where you're generating turbulent flow. Okay? Everybody understands turbulence flow, right? Reynolds number in excess of 2,000, okay, at least, right? And we are talking of much higher Reynolds numbers in these processes. So you have cavitation occurring, so air bubbles form because of turbulent flow, and essentially these air bubbles can collapse. Okay? They will not last forever, these air bubbles, because the pressure outside will cause these bubbles to collapse, the surrounding liquid. And if they collapse anywhere near the surface of the solid, right, such as the propellers of a marine engine, then they will generate, just like a laser interacting with water that generates a shock wave, this bubble collapse will generate shock wave. Okay? These vapor bubbles, when they collapse, generate a shock wave. They generate a shock wave, they also generate something called microjets. Okay? So you have water around it, right? So generate microjets. So combination of these two things can be strong enough to actually modify the surface. Not just modify, wear it, which is what happened in these marine applications. Okay? So what you see here in this picture is basically cavitation erosion. You're eroding the material away where these bubbles collapse. They collapse and produce such a significant shock wave that they wear the material away. And lots of these bubbles are collapsing continuously, right, over a period of time when this thing is operating. And you will have erosion, right? Erosion can occur. If you have used any kind of cleaning, water jet cleaning, you might have, in industry, people will use pressure washing systems, which have high pressure delivery of water to clean surfaces. Many of those probably are producing cavitation. Okay, that they're generating cavitation for cleaning. So what happens when you subject a solid surface, let's say a metallic surface, to such collapsing vapor bubbles, right, that have been generated somehow in a medium, in a liquid medium. So you have this water stream with bubbles in them, impacting the surface. Though it's not the water that is impacting with the surface that is causing this erosion. It's these bubbles that are collapsing, generating shock waves, and the shock wave and the microjets are strong enough to erode the surface. That's what's happening. So if you look at this plot, this plot shows you, and I know he said that he cannot record this, but so this is called mass loss. What happens when you erode material? Erosion means loss of material, right? So mass will decrease, right? So loss of material increases with more erosion. So this is showing you qualitatively how the mass loss rate, the rate at which material is being lost from the surface, as a function of exposure to these cavitating bubbles that are collapsing. Okay? So initially, the surface, there's some incubation time. It takes some finite amount of time for these bubbles to produce enough strain in the material to cause it to deform plastically, and then once you strain it all the way past the elastic, the fracture strain, it'll fail, right, and start eroding. So it takes some time, And eventually, so there is an acceleration period and there's steady state, and then eventually it'll attenuate. Okay? So this happens. Now, how do we take advantage of this? Okay? This is the basic principle. So how do I use it to generate residual stresses? Instead of using mechanical shocks, I want to use these bubbles, right? So if you look, this plot, mass loss versus time, initially there is, what will happen? The shock waves will deform the surface locally, pass the elastic limit, strain it, and once you remove the load, you will have some residual stress, right? So residual stresses will rapidly build up. If you continue to expose the same region to these collapsing bubbles, you're going to try to strain it more and more and more up to a limit, and then eventually you start causing it to fail. So that takes longer time. So now, if my goal is to erode and remove material, then I'll expose it to a very long time, or some finite amount of time depending on the material. But if I wanted to simply generate residual stresses, I will expose it to a much shorter time period, right? And I will generate these residual stresses, it'll saturate, then I stop. And this time is about anywhere from a 10th to a 20th of the time it takes for me to erode. So it takes a very short amount of time, okay? So that's the idea, okay? Now, I already said this, you can generate very high impulse pressures. Each of these bubble collapse events can generate on the order of gigapascals in terms of pressures, localized pressures, which is sufficient for you to deform the material, right? And you will also generate these what are called reentrant jets. These are micro jets that are formed as the bubbles collapse. They almost like collapse, and you can think of it as there is water coming, and between the bubbles there is a very small gap. The gap is reduced as the bubble is collapsing because it's shrinking. It'll speed up the water and produce very, very high speed jets, okay? Micro jets. So on the order of 500 meters per second, extremely high speeds. Combination of these two things can be taken advantage of to generate residual stresses using water, okay? That's the idea behind water cavitation peening, okay? That's the basic concept. As long as you understand that, nothing else matters. Everything else I say is extra stuff that even if you don't follow, it's fine. Now, how do you do this in practice, okay? So this is a process that's actually used. It's part of the standards for treating nuclear reactors in Japan. I mean, it's part of the standard. They use a process like this called water cavitation peening for treating, because a nuclear reactor is already in submerged condition. Liquid is there. So they want to do that, but not always with liquid present, but they can do it with liquid present without having to evacuate and stop the reactor and all of that. So that's one advantage. But it can be used for aerospace and other applications too. So a lot of the work was done in Japan initially. So what is happening? The easiest way to generate this cavitation phenomenon, you can actually generate even with a pipe. If you have a garden hose and you constrict the water flow to speed up the velocity of fluid high enough, and you shoot it at some dirt, you will see you'll clean it. That may be just water hammer impact, but if you generate enough turbulence, you'll actually produce cavitation there too. So there are very simple ways of generating it if you want to. So the simplest way here for industrial use, obviously you are not going to take a garden hose and try to do that in a manufacturing environment. So the idea would be to take a nozzle, right? Design the nozzle with some geometry, submerge it in some tank of water. So this is a stationary column of water. Oh, hold on a second. Again, I keep forgetting that he cannot record me. So here's a nozzle submerged in a tank of water. This tank of water is a stationary column of water. And you inject a jet of a water stream, okay? Typically it's called the inner jet, and basically at high velocities, right? On the order of 100 to 150, 200 meters per second type of jet. This jet interacts with the neighboring, as it comes out of the nozzle exit, it interacts with the stationary column of water and produces a shear boundary layer. It's a shearing process. There's a high-speed jet moving against a either a slow moving stream of water or not moving at all, in which case there will be a lot of shear. And that shear boundary layer will generate vortices and turbulence. Okay? And that turbulence will generate this cavitation because it will generate low pressure region inside the stream and generate these bubbles. Now this jet is moving down, let's say at the surface, and if you can design this process such that this cloud of lots of these bubbles, so this is a cloud, I'll show you some videos, they come and collapse at the surface. If you expose it for a sufficient period of time, right? Remember we talked about saturation and how long it takes to erode. If you expose it long enough, you will cause erosion like this. You'll have pits forming in the metal. So that picture is an example of a jet like this removing material. Okay? That's the principle. It's called submerged cavitation jet. Okay? Peening. This is one way to generate it. The other process that we'll talk about is a variation of this. Now the disadvantage of this is that if I want to do this on a large aircraft structure, okay, I need to submerge that aircraft structure in a large tank of water. That's not practical, right? I need to build such a big system to do it. It's expensive, not easy to do. But instead, if I were to take a high-speed jet and put it inside a low-speed jet, like a coaxial tube, think of it that way, right? Two tubes coaxially located, such that you have a low-speed jet and a high-speed jet. I can put this coaxial tube at the end effector of a robot arm or whatever, on the end of a machine tool, move it around anywhere. I don't need to submerge anything. That's the other variation that we looked at. Well, I'll talk about it. So anyway, this is the cloud that I'm talking about. Here's an example. This is from Professor Sayama and his group in Japan, which just shows you doing this, submerged, looking at this type of a process and generating this cavitating cloud. This is the cloud being generated, and it's collapsing in this region and causing this peening effect or erosion. If you expose it for too long, it'll erode. If you expose it for a shorter period of time, just enough to saturate the stresses in the material, you'll produce residual stresses. Okay? Same idea as shot peening. Sometimes people call this shot-less peening. There's no mechanical shot. That's why I call it shot-less peening. But anyway, the same idea. All right. Yes?
Is cavitation present normally in the fluid, or are we creating it?
You're creating it. You're creating it by injecting a high-speed jet into a stationary column of water.
Yeah. So like you said in propellants due to cavitation.
Correct. Correct.
So does it mean that the cavitation is present in the water, or
It's not.
created by the
It's created by the rotating turbine that actually is generating turbulence. That's what's happening. If just a stationary, the ship is stationary, the engine is not running, it won't cavitate. Okay? It might corrode, but that's different. Okay? All right? Okay. So, yes?
Sir, by what do you estimate that the process is done? Like, you estimated thing is being done, the target is achieved.
Oh, how do you determine?
How do you determine?
How do you determine? Mhm.
You concentrate that material for like this many seconds or this many minutes.
Yeah,
How do you
yeah.
estimate the time? For
That's not simple. You have to understand enough about the process. Okay? You have to understand the material. You have to understand the response of the material to the process. What is the process doing in the first place? Exactly how is it? What happens when these bubbles collapse to the material? How much does it deform? How long does it take for it to strain? All of these things have to be understood before you can say, okay, I need to expose it to X number of seconds, each point on the surface. That's a process design question, right? That comes once you have understood the process long enough. The same question applies to shot peening or any other process. You know, how do you know? It's not as simple as a machining where you say, okay, I need to remove a certain amount of material, I'll remove it. But there also you have to decide what feed should I use. Should I remove it in one shot? Should I remove it in 3 passes or 10 passes? You have to make those decisions. How do you make that decision? Based on what based on your understanding of what the process does to the material. Then only you can, and whether or not you're exceeding the limits of what the tool can withstand. Things of that nature, right? So those are questions one has to, yes, that's a fair question from a practical standpoint. In the end, I want to know, if I'm the user, I want to know how long do I need to run it, right? But that knowledge is what we are after in research. Once we have that understanding, then we can say, oh, I can dial in and say, this material, expose it under these conditions for this long. That's what's happening. Okay? That's where the scientific understanding comes in. Before you can blindly, you can do lots of trial and error. That would be the not so smart way of doing it, right? Ideally, as engineers, our goal is to use scientific principles to the extent possible and minimize all of that trial and error effort, which unfortunately in practice, you have to do that because these are complex processes. You can't model everything. You can't describe through equations everything that's happening easily. Not easy to do that, okay? All right, these are the reasons. There are some other reasons as well. Higher fatigue life can be generated compared to short peening. People have shown that. Limited surface roughening, that's important. Short peening, where you have mechanical shots impacting the surface, also tend to roughen the surface. Roughness is bad for fatigue life. So there's some optimization required there. You can tolerate some roughening as long as you have inducing sufficient compressive residual stresses. But water cavitation peening will produce less roughening and induce compressive residual stresses, okay, to a similar extent or even more. That's the other reason why you want to do it, in addition to some of these other things, right? The reusable, recyclable media, water can be recycled, etc.
So, is this method effective enough to be used for the composite materials, or is it restricted only to metals?
Yeah, metallic materials only.
Okay.
Yeah, composite materials will, so I'll show you an example at the very end where not for peening, you don't peen composite materials, okay? Composite materials, you cannot because they don't behave the same way, right? As they are basically have a polymer matrix, they have some reinforcement material that is inorganic or organic, and so they won't behave the same way. You cannot produce the same effects in composite materials, right? At least not polymer composite materials. Metal matrix composites, different issue, right? So
Any other methods similar to this used to maybe the same process, not the same process, similar methods which can be used as the alternative in the composite materials?
yeah, but the thing about composite materials, fatigue loading, I mean, you design the composite material to withstand fatigue loading rather than do some post-processing or surface engineering to achieve that end result, okay? Composite materials are lightweight, they can be strong and lightweight. That's what, lightweighting is what's driving their use, whether it's in aircraft structures or skin of the aircraft or in, high-end electric vehicles and so on and so forth, right, body of the structure. So it is not the same, none of these processes, I mean, your peening is not something people do, okay, for good reason, because these materials don't respond the same way like these metals do, okay? Yes?
How many alloy materials?
I'm sorry?
Alloy materials.
Alloys, yeah, sure, you can use for alloy materials, absolutely. I mean, metals, I'm not limiting myself to pure metals, alloys, yes. Yes?
Why not
What?
oil?
Good question. Indeed, people have tried oil, right? So you can. And some work was done here at IIT Madras a long time ago using oil jet cavitation peening, okay? Where you can use oil, and there are reasons which people have shown that oil, all the way from vegetable oil to other types of oils, can actually generate stronger cavitation phenomena because of the surface tension and viscosity of the fluid. They have an effect on cavitation. So yes, the short answer to your question is you can use oil too, right? But oil is more expensive than water, and there are other practical reasons why. And using oil, there are practical reasons such as the ones I mentioned that may prevent you from using it in practice.
I mean, we can't use gas or something.
Yeah, indeed, in injection systems for diesel engines, gas can produce cavitation too, actually. Okay, so, but gas phase, I mean, after all, these vapor bubbles are gas phase, right? It's a two-phase system. You have water and you have gas, vapor bubbles. So, indeed, but nobody has investigated using gas to peen metallic materials, because I don't believe you can generate enough sufficiently strong cavitation to deform the material plastically. But I haven't done it, so I don't know the answer, to be honest with you. Yeah. Yes.
During this process, heat will be generated, yeah?
Heat can be generated. Yes, heat can be generated.
When heat is generated,
Yeah.
the overall efficiency of this process will be also affected.
So cavitation as a phenomenon works best within a certain temperature range. So indeed, there's an optimal temperature range. So above a certain temperature, up to a certain temperature, let's say from room temperature to maybe 30, 40 degrees Celsius, there's a certain band in which it'll work well. Beyond that, it actually will enhance cavitation intensity. But beyond that, it will not. So yes, so you have to ideally try to, if you want to do this in practice, in industry, then you have to control that water temperature. Yeah, yeah.
So can we consider this water cavitation as a step ahead of the water jet?
In my opinion, yes, right? And that's one reason why nobody uses water jet peening in practice, to the best of my knowledge. Okay, people have tried it, but they don't use it because you need very, very high pressure systems to generate sufficient.
So one major advantage of this method is that the pressure required is less.
The pressure required is less, substantially less. There is less roughening. Cost is less. You can reuse the water. Of course, in water jet peening also you can reuse the water.
But cost, this works on a turbine, right?
No,
How do you?
a pump,
Okay, fine.
just a pump.
How do you generate pressure in the jet?
A pump,
Water jet.
a pump, a positive displacement pump or a pump, any pump, right? I mean, you are familiar with pumps. So all it takes is a pump, but it doesn't take a 60,000 psi or 100,000 psi pump. You can generate it with a 5,000 pounds per square inch pump, or you can convert that into whatever works out to be 35 megapascals or something like that, 34 point something pascals, right? So you don't need very high pressures, which means cost of the pump is less. I mean, you think of water jet cutting machines, those pumps are very expensive, okay? So you don't need that. The cost is less. All right. Okay, I think we are going very slow. Okay, so I'm not sure we'll go very far, but it's okay with me if it's okay with you, because a lot of the other stuff I have here are very too deep into the research, and for those who are much more interested in that, I'll point you to the papers and you can read them, right? Those who are interested in that. But I think given the mix of audience here, I think it's best that at least you walk away with the basic understanding of the principles and methods rather than very deep, intricate research details, okay? I mentioned another way of generating cavitation, which is easier, which is what we have focused on, is co-flow configuration. What is co-flow? One, I talked about submerged configuration, where you take a high-speed jet and submerge it in a tank of water. But that's challenging, right? And for large parts, it's challenging to do. It's easy to do, but if you really want to peen a large system, then large part, then you need some sort of a gantry system that moves this nozzle inside this tank, right? It's harder to do. So a co-flow system, which is the same idea, but you have a high-speed jet that is injecting high-speed jet of water into a column, but it's a moving column. It's not a stationary column of water that is surrounding the high-speed jet. And that low-speed column of water is generated through this coaxial pipe, right, around it. So You still have the same principle. This high-speed jet interacts with the low-speed jet, okay, generates shear or turbulence, generates cavitation, and moves this, right? Same idea. The thing is, this process people have not investigated a lot. So about 10, more than 10, 12, so around 2010 or so, we said, okay, well, this sounds interesting. This is a practically relevant process. I can put this on the end of effector of a robot arm or a gantry and move this around. So it's, from a practical implementation standpoint, it's easier. Or I can do it on a machine tool where already I have an actuation system, right? XYZ motion is there. You also have coolant in a machine tool, which is a oil-based emulsion, water and oil, right? And I can machine the part, and then I need to peen one region of the part. I can simply change from a cutting tool in a CNC machine to a nozzle and use the fluid to do it. That is our idea. That's where we started. Industry did not like that idea because they say, well, I buy a machine tool to cut metal, not to peen. So that is their practical reason. But to me, as a researcher and a scientist, hey, that's practical. I can do it on the same platform, both. Produce the part, peen it, right? So, but anyway, that's where we started. So we can do this much more easily, and that is our reason, but the scientific understanding was not as deep available in the literature. The Japanese had done some work. So we started looking at this, and here's a video that shows you the co-flow cavitation phenomenon. It's a high-speed video of the cloud forming and dissipating. You see that dark region in the center, and you see the low velocity fluid around it, the column. That's the coaxial flow, low speed jet. High speed jet is that center one that injects the water, generates this cavitation cloud. There are lots and lots of air bubbles. You cannot see how many. We don't know. That's the unknown part. It requires very sophisticated ways of actually trying to see what's inside. Those go beyond even what we can do. I mean, there are people in fluid mechanics who will do some sort of imaging techniques to try and understand it, but it's still a research issue. But nevertheless, I can generate this. You can see this pulsation or pulsating cloud formation and dissipation, formation and dissipation. And you see some oscillation as well, right? And so if I place the part, the surface that I want to peen, at the right distance, where I have the strongest cloud, let's say the largest cloud, which hopefully has most of the bubbles, okay, and make it collapse, and then I should be able to alter the surface, right? Modify the surface. That's the idea. So this is what we start looking at, and if you expose it, in this case, this is some aluminum. It's been exposed to that at one point only. After this saturation time and further exposure to incubation time, now you start removing material, and that it accelerates, starts eroding very rapidly, right? And so it results in something like this, like a central region and an annular region of removal. Okay, this is what happens in this type of a process. Now, of course, the goal here is not to erode, although that could be a reason. You want to prepare the surface. I want to actually first roughen it, and then I want to peen it. Then maybe coat it or something. You can still use this process for that, as I'll talk about later on, hopefully if you have time. So, yes?
According to the need, is there any mechanism to vary the pressure?
Well, you mean intentionally vary the pressure? Well, you will have to vary the pressure at the pump, basically. Now, there are ways of varying the pressure by designing the nozzle as well. So if you have a fixed pump and you want to, let's say, intensify the cavitation, right? You want to make it stronger. So I can peen more difficult to deform metals, titanium alloys, some other super alloys or whatever. Then you need stronger, the bubble collapse events have to generate much stronger impulse pressures. You can do that by designing nozzles, okay? So this is where the intellectual property lies. The creativity is in how you design the nozzle, okay? That's one way of changing the pressure, characteristics, okay? So, yeah, that would be the way, yeah.
So when we compare this one, co-flow configuration, is that advantage has is only the time variation?
No, I think it's the flexibility of the process relative to the submerged case, where I need to have a tank, right? Here I don't need a tank, right? So it's more flexible. I can move it around anywhere I want. right? We even built a handheld system. I'm sorry?
And robot end effectors.
Yes, yeah, robot end effectors, you can, however you want to implement it in practice. So those are practical advantages, but in theory, it's possible to generate even stronger cavitation. People have shown some work, show that stronger cavitation than even submerged. But based on my own experience, I believe that submerged is the easier one to implement. Okay, so all it requires is one high-speed jet in a tank of water. If I want to do basic studies, I can do that. Right? This is what Soyama and others in Japan did much of the work on submerged cavitation peening. Yeah. All right, so you know what? I'm not. There's work in the literature. Okay, there's a lot of work has been done in submerged cavitation peening. So I won't go into all of those details. I think in the interest of time, again, like I said, nozzle design is key. Okay, so there hasn't been a systematic study on, or there have been some for sure, but systematic study for the core flow case, at least. You know, Japanese have done work on nozzle shape and dimensions, on how that affects the peening characteristics and so forth. You can find some literature, but systematic study was required. Or they don't give you all the details, so you don't know what if they don't give you the geometry, you don't know what pressures were generated, what velocity, or pressures given, velocities are not known, etc. So that motivated something, and then there's more work that has been done. You see some of the names, so I won't. This is less important. This sigma, by the way, is how you characterize cavitation intensity. It's called the cavitation number. It's the pressure differential. You know, this is the pressure at some point in the flow, minus the vapor pressure, right? At a given temperature, the vapor pressure will change with temperature, divided by the kinetic energy of the flow, right? Now, that's what that is. You know, half rho times u infinity square is the velocity at the nozzle exit. It's the kinetic energy of the flow. So the pressure over the kinetic energy, pressure differential over the kinetic energy gives you a number. It's a dimensionless number that tells you something about how strong is the cavitation? How likely is it that the flow will cavitate? That's what it's telling you. Sigma, the lower the value of sigma, the more likely, okay, that cavitation will occur. That is the basic understanding. Lower the value of sigma, the more likely cavitation will occur, right? So you want to drive down sigma value, okay? So people use that as a metric. So these are some of the limitations, you know, effect of nozzle dimensions, can you scale this process, what is the effect of jet velocity, all of those things. When we started looking into this process, not known, so that motivated us. And then we, of course, our goal was, can we eventually model? Can we model this process, design the nozzles through, engineer the nozzle shape, etc., to generate cavitation intensity in a predictable manner so we can, you know, optimize the process and implement, right? That's our goal. So we built a system. Now you can't buy these systems, right? You can't buy these machines, at least to the best of my knowledge. Maybe there's somebody who will make it for you if you give them enough money, and tell them how to design it. So we had to go design it ourselves. Of course, like I said, you can take a water hose, a garden hose, and generate cavitation, but that's not an industrial system, right? So we built our own system that you see a picture of. There is a tank of water. This is the tank. There are two pumps. There is one pump for the high-speed jet, and there is one pump for a low-speed jet for that coaxial flow. Inside this chamber is where the flow comes through here. Down here, there is a nozzle. This is a cross-section of the nozzle that you see here. This is the high-speed nozzle in a velocity. This is the surrounding low velocity region, right? And that chamber is where you do the peening. It's on a gantry system, so you can actually, you know, program it to move different points, different speeds, and peen a surface. Right? In the end, in practice, you would be doing it over a surface, not just one place, one location. Ideally not. It gives you some numbers, you know, 34 megapascals, which is about 5,000 psi. You can generate. It doesn't require a very expensive pump, right, to do this. For the low pressure pump, it's even less requirements, so easy to do. The design of the nozzle looks like this, the tip of the nozzle, okay, this region. This is where we started. There are a lot of variables. This is why one has to, I mean, we did this experimentally, but after a while we realized that there's infinite combinations. And that's not very practical to do it. But the problem with doing this to modeling and simulation, and people have tried it, is you need to do computational fluid dynamics type of simulations to simulate turbulent flow, which is not very easy, even according to the fluid mechanicians. So cavitation simulations, while you have CFD tools today that give you some capability to do these things, you have to be a real expert to know whether what it's doing is correct. Okay, that's the danger. You can use a software blindly, very dangerous. You have to be able to analyze and understand, is it doing this? Just because it's solving the the Navier-Stokes equations some way, there are many ways to solve it, doesn't mean that it's doing everything. So this is what we realized. But anyway, we did this experimentally first. Here's high-speed imaging, okay, of the flow coming out of that system, and showing you what happens when I change the velocity, the inner jet velocity, right? That inside pipe through which I'm injecting fluid, water. So from 50 meters per second to 150 meters per second. And what you see clearly, and the outer velocity, the surrounding low speed column of water is at 11 meters per second in this example, right? You can see here that the cloud forms and dissipates. At low velocity, inner jet velocity, it forms and dissipates very quickly. So if I had to actually peen using that, I'd have to keep the surface very close to that exit of the nozzle. But as I increase the inner jet velocity, the size of the cloud varies and increases. Of course, if I make it, this is the greatest. If I go beyond this, I may be able to. We had limits with our system, but you can see here, as you go from here to here, there is greater disruption of the flow. You can't go too far out. You can't put your surface here because already this entire flow is dissipating. You know, what is happening is that inner jet is accelerating the outer jet, right? Because the inner jet is moving at 150 meters per second, outer jet is moving at 11 meters per second, accelerating it, and eventually it destroys the flow characteristics. So yes, I can generate very thick clouds of cavitation, but then the distance to which that cavitation cloud can be carried by the flow is limited. Okay, that's what it means. What happens when I keep the inner jet velocity fixed at 150, because 150 gave me the highest, right? Largest cloud, what looks like visually to me a strongest cloud. I vary the outer jet velocity. And you can see here that, you know, at very low velocities it's problematic. You completely destroy the flow and it, you know, essentially dissipates. And it improves a bit, and then at about 11 is where we picked as the best case. After that, you can see, you know, it's okay. You can do this as well at 15 if you'd like, but you generate the strongest cavitation clouds at combination of 150 meters per second inside jet velocity and 11 meters per second for the outer flow. Okay, so that's our optimum. Okay, in our case, right, for our design. So what happens now? You take these parameters in our system and expose it and run some tests to understand the scientific understanding I was trying to tell you about. That hey, look, I want to understand how strong is this jet, how much can it peen, how much residual stress can it generate, right? Now the easy way, residual stress measurement is not easy. You know, residual stress measurement can be done, the way we did it requires X-ray diffraction. It's expensive to do, time consuming to do. You can also do using hole drilling type of methods, but they're very difficult to do. I mean, they take time. So I don't want to waste my time doing for all different combinations X-ray diffraction. So mass loss is a metric that is used. There are standards, ASTM standards, that tell you that for cavitation you can use mass loss. Okay, mass loss is how much, instead of peening, we are eroding. I expose the surface to an extended period of time, I erode material, I see how much material I eroded. Obviously, if the cavitation is stronger, I should erode more. There should be more mass loss, right, intuitively. Which would mean that, hey, if I don't expose it for that long, I should be able to generate more residual stresses quicker, right? The same idea applies. All right, so it's easy to measure mass loss. I can just take a scale. I can measure the starting mass. I can then expose it for a certain period of time and then measure it again, see how much mass was lost. That tells me under these conditions this is what happened to the material. right? So this is what we did as a function of the flow velocities. This is the outer flow velocity, and this is the inner flow velocities, right? And this is the mass loss in milligrams of, in this case, aerospace grade aluminum, 7000 series aluminum. And you can see here that 150 meters per second, clearly there's an optimum from these trends. Not every combination gives you the best result, but generally what we can see is that 150 meters per second inner jet velocity and 11 meters per second outer jet velocity combination gives me more or less the highest, okay, with our system. So, okay, now what happens, how do I quickly test without having to do residual stress measurements using X-ray diffraction? How can I tell that under these conditions I will generate more or less residual stress? How do I evaluate that effectively? One way to do that is using strip curvature measurements. Now, if we take a strip of metal, let's say aluminum in this case, and subject it to, let's say it is stress-free to begin with. Let's say it's annealed, and you have done some stress relieving on it. So you're starting with material with no inbuilt stresses or minimal inbuilt stresses, and then you subject it to this process, and you don't erode, you only peen. You peen for a short duration, so you saturate the residual stress, right? That's the idea. And what will happen? If there are sufficient residual stresses you generate, then residual stresses will lead to distortion. Because what are residual stresses? They are stresses, elastic stresses in the body that will equilibrate, right? They'll adjust, and to adjust and make sure that the material doesn't break, it'll adjust its shape, okay? And you can show that from just basic elasticity theory, that's what happens. So you measure the curvature. The greater the curvature means more residual stresses in the material. That's simple to do. I can measure the geometry or the change in shape. This is what people will do in practice as well, okay? So here it shows you for those same conditions what the strip curvature is. The curvature itself is greatest for that 150 meters per second inner jet velocity and 11 meters per second, suggesting that under those conditions I generate the highest amount of residual stress with our system. If you have a much more powerful system, maybe you can do more, but it gives me an understanding of how these two knobs of velocity affect residual stress generation, right? What happens to the roughness? Roughness is bad. Too much roughness is bad. So while I will generate more residual stresses, I'm also roughening the surface because these bubbles, vapor bubbles, are collapsing and deforming the material plastically. So what happens if you take a marble that you all have played with at some point and take a soft metal and throw it at it, you'll produce an indentation. But if you zoom in on that indentation, material will have plastically deformed on the sides, right? It'll produce a ridge, material flow. Okay, well, that is roughness. You're roughening the surface. It's no longer flat. So you don't want too much of it, but that's what's happening. But you can see that the roughness is higher under those conditions compared to the other conditions. But okay, the question is, how does it compare to other processes? Yes, you're producing some roughness. Hopefully it's less than the worst case or the best case for the other processes. Then I can justify this is a better process, right? So we did that, and you see here, this is roughness of the received sample, the aluminum sample. This is the maximum roughness we generated with our system, okay? Worst case at 150 meters per second and 11 meters per second outer jet velocity. This is data from literature for the same material using shot peening, mechanical shots. That's the traditional process, where the least roughness is worse than the best, the worst case roughness in my case. So that suggests that yes, while you do some roughening, it is not as bad as the other process, right? So that's a promising result, at least. This also shows you the residual stress distribution, these elastic stresses in the material measured through X-ray diffraction. And you can see here residual stress. You can see it's very deep, it's compressive. This pink colored curve, it shows you it's deeper. This is data from literature using shot peening, okay? They are similar, and I'm not saying they're substantially different, but you can generate using this type of a process where you're using water and recyclable media and all of the other advantages that we talked about, right? So this is what it shows you, right? You're able to generate deep compressive stresses. Generally, this hook-shaped residual stress distribution is what is desirable for fatigue life enhancement. Okay? All right, yes?
So the x-axis represents the depth of the material. That means it is going subsurface.
Yes. Yeah. So this is subsurface. It's going from 0, which is at the surface, down to about 400 microns below the surface. And this is done through X-ray diffraction by, electropolishing, removing layer by layer, few microns at a time, measuring it again. And then these data points are ones that generated. Okay? Yes?
So this sigma 1 is the periodic component of the stress?
This is basically the stress component in the direction of, in this case, if this is a surface that actually was peened, right? So this is actually in this in plane stresses, in plane stress component. Okay, these are elastic stresses. Deviatoric stresses would essentially be what generated the plastic deformation.
So actually this any process leads to the plastic.
Correct, correct. But what we are measuring are after you removed all loads. So what is remaining in the material is elastic stresses. And sigma 1 is the x direction principal stress component.
So one more question.
Yeah.
So while modeling the residual stress, we need plasticity model.
Yeah, you do need. You do need.
Plastic deformation.
Mhm.
So which plasticity model we should consider?
That depends on the material. That depends on the material.
That's since material is going under plastic deformation.
Yeah, sure.
It might have some stir rate.
Of course.
So how we can measure what is the stir rate so that we can choose the appropriate plasticity?
Yeah. People have actually looked at deformation rates in cavitation. These are very high strain rate processes. The localized bubble collapse events are occurring over very short durations. So the material is being strained over a very short time. So these are high strain rate. You're talking of probably at least on the order of 10 raised to 3 per second type of strain rates, probably. Maybe even higher. Okay?
If it is more than 10 to the power 5, we generally consider Johnson.
Yeah, well, Johnson-Cook is one constitutive model only, right? It's only one constitutive model. It's a purely empirical model, right? You can use Zener-Holman. You can use many other types of constitutive laws, right? Flow stress rules that material models. So yes, you can use Johnson-Cook, or you can use Zener-Holman, or whatever.
We are following the correct model.
That's all. That is the criteria. You need to make sure that the constitutive response of this material follows, the model you use follows the constitutive response or fits the constitutive response. That's all you need to make sure. Yeah. And there are many models. It's not just one. Yeah. Okay. All right. So we are actually technically out of time, and I have not even scratched the surface here. But in the interest that this class has to end on time, I'm going to stop here because I think my intent was to make sure that I not just throw at you 100 slides, which to me is useless, right, if you don't understand half of it. Let's stop here. Let's see if there are any other questions you have. But I'd rather stop here, and there are papers, there's other things that I can point you to that you should go read to get a deeper level understanding if you want, including our own work. Because other things are, okay, what did we do? We tried different nozzle geometries. We tried other things. Can we modify the nozzle geometry to generate pressure fluctuations, like the question was asked? We've done those kind of things. Those are details, okay? Those are details. And I want to make sure that for those interested in those details, I'll point you in that direction. You go read the literature. But as long as everybody understood the rationale for the process, the basic principle of the process, how do you go about deciding why we should study this process, etc. I think I feel that would be the more important takeaway for you to have than become the expert on cavitation peening. You cannot be an expert. I'm talking about stuff that was done over 15 years or something like that, right? Which you cannot do it in 1.5 hours, right? So I'll stop here. Any other questions?
So which material we are using?
7000 series aluminum. 7075, which is an aerospace grade structural aluminum. Yeah?
So generally, I have studied laser shock peening to some extent. that peening process, we generally are concerned with the overlap percentage of the
Yeah.
peening.
Indeed.
So any research was done here to optimize that?
In all of these, where we are measuring residual stresses and we are actually peening samples, there is an overlap ratio that we determined. We quantify it in terms of exposure time. How long? Because it's the exposure time that matters for us. We don't want excessive exposure to cause erosion. We don't want erosion, right? So we computed, the publication tells you how to determine that exposure time for each point. And based on that, you determine the overlap between passes. Yeah. Any other questions?
So,
Yes.
he asking, will there be any chips formed during the process of erosion, and will that affect the process here?
If you're eroding, then yes, material has to go somewhere. You will produce debris. It'll be in the water. And that's not a good thing. This is probably strain-hardened material that can get entrained in the water and can cause further erosion or erode your pump, can damage your pump. Right? This material, water is being recycled. So you don't want erosion, ideally. So you need to have filters. In our system, there's a filter that tries to filter out any particles that might have been generated before it goes into the pump. So those are all practical precautions you have to take. Yeah. I think somebody asked me earlier on, and let me just script this. I had more slides than, but I tend to go slow. I'd rather, because this is like a classroom. It's a course. Not just we cover everything and you understand nothing. So what else can you do, with this process? Oops, sorry. This process you can, like paint stripping, okay? Because I can erode with it, or I can peen with it, and usually when you're doing maintenance and overhaul of critical components like jet engines or whatever, you have to take an operating engine out of service and you have to clean up, remove paint, strip paint from it and peen. Or it could be the aircraft structure where the wing meets the body, where those are critically stressed components or joints, and then you have to strip the paint, you have to resurface it, and then you have to recoat it, maybe peen it again and then. But now you have a process which can do all of them. You can actually use this process in erosion mode and erode the paint, remove the strip, the paint that is applied. So now you've exposed the bare surface. Now you can peen that surface by turning different knobs on the same process, and then you can go ahead and paint it back. So that's another application, right, of this process. You can also, one of the other things we have worked on, including recently, is can I use, this is water-based. Now think of, for those of you interested in additive manufacturing, metal additive manufacturing, which is where much of the research is today. Additive manufacturing captures everybody's imagination. Oh, I can make anything. Yes and no, okay? So the reality is that the quality characteristics of additively manufactured parts are not where they need to be as built. You have to do post-processing. You have to actually improve the surface finish. You have to maybe increase the density. You have to maybe increase the mechanical properties, enhance the mechanical properties. All that requires subsequent processing. Now think of additively, what is the reason for people to use additive or 3D printing? Because you can produce very complex shapes, right? I can produce hollow sections inside easily. I can produce lattice structures, very complex structures. Think of lattice structures or internal manifolds. Those kind of features, how can I finish the surface of internal surfaces? How can I not only finish the surface, improve the surface finish, but also improve the mechanical strength of that inner surface? I can't even access it once I've built it. Now, if I have fluid, I can force through, and it can do both finishing and it can do also peening, then I can alter both. That's the idea. So we've taken that and done this at a desktop level by combining a process people actually use to finish metal additive parts, such as electrochemical machining or electrochemical polishing, because that's a fluid. But use peening, cavitation phenomena, combine the two to produce a hybrid process. I just don't want to improve the surface finish. I want to do that. Plus, I want to quickly also at the same time improve the mechanical strength, okay, of the surface layer. So it'll enhance its mechanical properties in regions where I cannot access easily once I have built the 3D part. So those are other types of applications that you can use same physical principles or extended versions of those principles by combining electrohybridization. Professor Samuel talked about that a bit, right? He showed this big machine where you can do almost any machining process. Well, same idea, but now you combine electrochemical polishing with cavitation peening to do both faster. It's not just combining the two things. You know, you can combine many things. Well, why should I? I want to combine. If I combine 1 and 1, I should produce 3. Then only it makes sense. If I still do 1 plus 1 is 2, then okay, then I can do that sequentially. I don't need to do it together. So that's the reason. And there are reasons to show that you can actually you can do things faster by combining it in this way, actually. So those are two applications of, you know, the basic principles I talked about, but for very different applications, right? One is for paint stripping, and another is for improving the surface quality of metal additive parts that have been produced.
So in this,
All using cavitation phenomena. Yes?
So in this particular application, you used LPBF parts or which process?
In this case, is selective laser melting.
So in that case, we generally use sandblasting to finish the metal parts after we get it from the print. Can we adopt the cavitation process?
Yeah, so you have to, cavitation alone to do erosion and peening simultaneously is probably not a practical solution. It'll take you much longer. So that's why combining with electrochemical polishing or sandblasting. So what you can do, which people have tried, is combine cavitation peening, as I described, but train in the flow mechanical shots. That's shot blasting, like you said. Combine the two. Then you can do it faster. You can, because the shot will remove the roughness much quicker, and then the final finishing and improving the mechanical properties, it'll do both. In that case, it'll do both. Both processes will do both. Yeah. All right. Yes, go ahead.
Question, sir, that residual stress of grinding source, sir, is it during the process or after?
No, afterwards.
So then why it is elastic stress? Kind of plastic stress.
What is the definition of residual stress? I thought we talked about it.
That is the locked stress.
Locked in stress, after you've removed all loads. What is the nature of this locked in stress? It is, the cause is inhomogeneous plastic deformation, yes. But what is left there are elastic stresses. They're elastic stresses. No, what I'm saying is that the reason you have residual stresses, the cause is inhomogeneous plastic deformation. That is non-uniform plastic deformation. That is the cause, yes. You need that. But residual stresses, after you've removed the cause, which is the thermomechanical loads, what is left in the material after you've removed everything would be, these residual stresses are essentially elastic stresses. So if you want to simulate, you do need a plasticity model, of course. Of course you need plasticity model, of course. But those stresses are elastic stresses in the material. All right, we'll stop here because we are about 15 minutes past our end time. Okay? All right, thank you.